So today the section is called reflexive space. So what are reflexive spaces? So here is the definition. So assume that E is a Banach space, and J is the canonical injection from E into the dual space of the dual space. So we know that E, we've seen that E is included in the dual of the dual. In fact, J of E is included in the dual of the dual. And so J is defined by setting. So for each x in E, you associate phi of x or phi x in the B dual by phi x of phi. This has its value on K, and it's equal to phi of x. And so now with that, we can define what is a reflexive space. So a Banach space E is reflexive if J of E is the dual of the dual, meaning that, in fact, J of E is onto or surjective. Okay. So this is well defined. We already seen that you have this inequality. So this says that phi of x belongs effectively to the dual of the dual. Okay, so we are not studying that here, but in fact you can prove. So a good reference for that is the book of Brazis, right? So, and actually we follow we follow some parts of the book of Brazis. So, but so that the remark 35, we are not going to prove that, but so LP, either capital LP or lowercase LP, for P between 1 and infinity are reflexive, but not capital L1, capital L infinity, and lowercase l, and here there's a typo, it's lowercase l. They are not reflexive. Another example, and that we will see in the next chapter, is that Hilbert spaces are reflexive. Yeah, so we are not going to deal into that. I refer to the book of Brazis to why. If you have time, if we have time, but I doubt so, we can discuss that in another lecture. Okay, so what we are so there's a question in the chat for what's basically the distinction between K and C. Well, everything we've done is valid for C. Unless mentioned explicitly. So everything we've done is always for a general K, where K equals R to C. So everything we've done in specifically the question is valid for C. Okay, there's also a chapter on that on Brazis, on the English version. I don't think it's on the French version. So there's a whole chapter, short, a whole section, a short section, which emphasizes the difference between R and C. And yeah, so the previous professor at Le Havre University of these courses was really a specialist of complex numbers, and so we need to include C, but okay, and that's classical to include C, right? Okay, so what we are going to do today, we don't have time to do a lot of things in for reflexive space. Again, there's a bunch of results in Brazis, and I have also provided another other references. But the theorem that we are going to deal with today is the following one. So a Banach space is reflexive if and only if the closed ball so the closed ball by definition is the usual closed ball in the Banach space. So it's the by analogy with Rn or so with the norm, right? You have a Banach space, meaning you have a complete space with a norm, and this is the regular norm, the usual norm, right? So this is defined with the regular norm, but it will be reflexive if and only if it's compact, but for the weak topology, because as we discussed yesterday, yes, so for an infinite dimensional Banach space, BC is not compact for the regular topology associated with this norm. But if it's compact for this is the weak topology, then it is reflexive, and vice versa. All right. Okay, so we are so this lecture is devoted to the proof and explanation discussion about this theorem. So we are going to prove this theorem, and so so it's an equivalent. So we need to prove first that if our Banach space E is reflexive, then the closed ball is compact for the weak topology, and conversely, if the closed ball is compact for the weak topology, then our Banach space is reflexive. So what do we know? We know so what we saw last time is that so we saw that if I call BC in the is second, we saw that it's compact for which topology? Can you say for which topology? So it's a weak star topology, but it's a weak star topology in E second. So it's this one. All right. So if we apply the theorem from yesterday to E second, we say we know that the unit ball is compact. For this topology. All right, so so if you assume that that J of E is E second, you have also that the J of B, so the image of the closed ball, the unit closed ball in E, it will be the unit closed ball in E second. And so if I want to prove that my closed ball is compact for the weak topology in E, it is sufficient to prove that J minus 1 is continuous. So therefore, so to prove the result, so the result is what? Is that BC is compact for the weak topology. It is sufficient to prove that J minus 1, you know, because the image of a compact by a continuous application is a compact. So that J minus 1 is continuous. So we need here to be clear with the topologies that we are working with. So from so E second is endowed with this topology, and I know that B is compact. So the closest unit ball in E second is compact for this topology to E endowed with the weak topology here. All right, so now to prove this, I will recall you a general thing. So let's do some. Let me do some comment here. So in general, if you assume that you have, let's say, a topological space Y with a topology Y, and then you have the topology X with, this is a topology associated with so tau X is a topology. It's an initial topology. So you have some applications, some functions, phi I or whatever. So you have some applications phi I in some other space. So let's write it like that. So you have also EI or even XI And so here, tau x is the initial topology associated with my phi I. Okay, then this is a little exercise. You can say that. So if you want to prove that an application phi is continuous from y to x, this is equivalent to prove that for all I, my phi I, and I take the composition with phi, capital phi, is continuous. So here from y into xi, and here okay, so that's a general result. You can prove that as an exercise. So what I want to do now is to prove that j minus 1 is continuous from this space with the associated topology into this space with this given topology. And so here, my functions phi are given by the phi in this space. So if I apply that here, what do I obtain? So try to figure this out. Now, so we want to prove that j minus 1 is continuous from E second to E with the respective topologies written. So, but to prove that, that's classical results from topology. It's the same that proving that for all phi corresponding to this topology. So for each phi in the dual space of E, when I compose phi with j minus 1, I obtain a continuous function, but this time from E second into K. This goes from E second to K. So is that right? So let's figure out what's exactly is that. So if I pick up, so here I pick up a x in so each E second, so it corresponds to a x. So if I write the phi, I compose phi with j minus 1 associated with a phi x. So by definition, this is phi of x. Okay, so for example, if I look at the reciprocal images of open sets of K with phi, this is the same thing with the reciprocal images of phi composed with j minus 1. But we know that phi is continuous from E into K. So we know that phi is continuous. And so that's it. So we have proven that if my space E is reflexive, then the closed unit ball of E is compact for the weak topology. Now we want to prove the converse, that is, if the closed unit ball in E is compact for the weak topology, then X is reflexive. So to do that, we will need two lemmas, the first of them being the lemma of Helly, and it says that if E is a Banach space, for any phi 1, phi n, for some n, and phi I, phi n, so a finite numbers of elements of the dual, and for all gamma 1 till gamma n in K, the two properties 1 and 2 are equivalent. So the first says that for all epsilon positive, you can find x epsilon in the closed unit ball of E, such that phi I of x epsilon is closed with gamma I at the distance less than epsilon for the distance in K. Oh, there's a question, which norm in 2? Yeah, okay. And this is equivalent to for all beta 1 and beta n in K. You have that. So beta I in K, gamma I in K. So here it's the norm in K. So in K it's R or C. Okay. Is less than, but now this is the norm. We work with only one norm here. It's the norm of the dual space. So phi I are members of my dual space, and this is the norm in the dual space. Okay, so we are going to prove this lemma. Yeah, so to obtain one, that one implies two, you start from there. Then we want to introduce the phi, and the way to do that is introduce it like that. And now I can use my assumption of one, meaning that I can approximate gamma I by phi I of x epsilon for any epsilon with x epsilon in the closed unit ball of E. All right. So, but if I write that, I need to also add this one, so that the two sides of the equation are equal. Okay, then here I apply my assumption in one. So this distance between the two are less than epsilon, and I obtain that. The other term is given here. I let it as is. So finally, I get that, but so the sum of bi phi is in the dual space, is in E prime. So by definition of the norm in E prime, I got that that this quantity is less than the norm in E prime times x epsilon, but this is less than one, so I can just get rid of it. And so if I let epsilon going to zero, because this is true for any epsilon, I obtain the results that we are looking for. So we need to prove that 2 implies 1. So what's the meaning of y of 1? Sorry. So next, we need to prove 2. So assume that 1 is not true. This means that there exists a positive epsilon such that for all x in the closed ball in E, you have that so sorry, this is not a norm because this is the module in K. It's a norm, but is more than epsilon. So this means what? This means that, so for example, let's phi, just if I call it gamma, and let's phi of x epsilon b sorry. Okay, this means that the norm of phi of x minus gamma is more than epsilon. And here, this is the max norm in k to the n. So this means what? This means that that in fact we can separate and gamma. And so meaning that, so there are several ways to doing that. So then you can prove that you can find beta 1, beta n, such that, so in the way that you want, the sum from 1 to n of beta I, gamma I is strictly more than some value alpha. And here the sum over beta I phi I of x. Yeah, you can find that. So I give you an exercise. So find explicitly, this is for next time, find explicitly the values of beta I for k equals r and k equals c. Okay, but so this is related with the certain forms of the unbanal geometric theorem. So you can find that. So I'm not going to do it, but find explicitly those beta i's. Okay, that's an exercise. Okay, so once we have that, I obtain a contradiction. Okay, so yeah, the idea of the 2 implies 1 is that you can separate. So if I do, for example, in R2, you can separate the image of the ball in R2 with your gamma, so that you can find some hyperplane that separates the two. And so here it's I wrote the case for the general complex case, and this gives you the result. All right, so so we're done with the first of the 2 lemmas. So we proved our first lemma, and then we are going to prove the second lemma that we need for the proof. So assume that E is a Banach space, then J of E is dense. All right, you can prove that. If E is a Banach space, then J of A is dense. So if I talk about density, I need to provide the topology, and so the topology is sigma of E second E prime. So let's prove the lemma. So to do that, yes, it's sufficient to prove that that the image of the closed ball, the unit closed ball, is dense in the unit closed ball for E second. And the density, so the density is with respect to this topology. So what's the meaning of being dense? So you will pick up some G in so you pick up some G here, and any open set for this topology such that G belongs to the open set. So, but we did this a couple of times. By the definition of the topology, then you can find a set which is included in U that writes like that. Okay. This is because the initial topology is defined thanks to finite intersections of reciprocal images of K. Okay, so if U is an open set in this topology that contains G, then you can find a finite numbers of linear functionals in the dual space E prime, phi 1 till phi n, and some epsilon such that such that the in fact the balls centered in phi so this is the reciprocal. This is a reciprocal images of the balls centered at phi I of G and of radius epsilon. Okay. And so to summarize, so this set is included in U. Okay. That's come from the definition of an open set for this topology. But that's very good. That's very good because this looks like the point one of my previous lemma. Because so now we want to prove that the J of BC is dense. So we want to prove that there exists a X in BC such that X is in this set. So that's what we want to find. We want to find an X. It's not in E, it's in BC here. There's a typo here. It's in BC. We look for X in BC such that this thing is verified. But this is exactly the point one of my previous lemma if I call this quantity gamma I. Okay, and from the previous lemma, proving this is equivalent to proving that that this is true with gamma I equals phi I of G. Okay, but now if I replace gamma I by phi I of G, this will be true because G is in the ball. So now let's write this like that. Okay, but this is true. Because now there's some typos here. I'm sorry. So here I need to close here the modulus. And so by the definition of, since BI phi I is so BI phi, the sum of BI phi I belongs to E prime. And so by definition, this is less than norm of G times the norm of the sum of BI phi I. And then I can get rid of the G because norm of G is less of 1. So finally, I obtain the point 2 of my previous lemma, which gives me my point 1. And that's what we wanted to prove. So we're done with the lemma 4. All right, so we are now able to end the proof. So the first thing is that the canonical injection J is continuous. Okay, it's continuous. So the argument we already see that. So saying that J is continuous from E sigma E prime into E second sigma E second E prime. It's the same to prove that I can look at composites by any phi in E prime and this works because phi is continuous from here to here. Okay, so we're good now. By assumption, BC is compact. So since BC is compact, then the image of J is compact because we just proved that J is continuous. And since J of BC is compact, it's closed. So J of BC equals its closure because it's closed. But we've proved that J of BC is dense in BC is second, and so we are done. That's what we wanted to prove. Okay, and once we prove that J of BC is second, this means that J of E is second, and so we're done with the proof. That means that E is reflexive.